Hello, hello. Oh, I just lost my board again.
Hello.
Oh, hello. Hello. Hello, Eugene. Hello, Remy. Hello, Ashton. Sorry. Hello.
Hello.
Hello, iPhone. Wait, iPhone, I know. Oh, hello, Oh, how'd you just do that? Oh, wait. Wait a minute. That's really confusing. Wait, is Remy with you? Is that Eugene and oh, that's so crazy. Okay. Hello, hello. Good to see you. And oh, and that's wait, sorry. Okay. And hello, Sulady. Hello. Wait, all right. Um, we haven't even done anything. I'm already behind. Hi, Ariana. Hello, Dewan. 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 Hello, Jonathan. Hello, Sulady. Hello, Abigail. Good afternoon, Sylvie. Hello, Ashley. Hello, Kayla. Hello, Giselle. Hello, Marina. Um,
Hello.
hello. Oh, it's even all right. That's like a double. That's like 50 points of class participation.
Yay.
All right. And hello, and I see, and I see
Does
Ashley.
the cute dog get me extra points?
That's interesting. Yes, maybe, possibly. Except we have a cute dog here too, and it kind of drives me crazy. I have mixed feelings about cute dogs right now, so I'll have to take that under
In
advisement.
the avatar.
Yeah, no, I know.
I mean the Zoom avatar
No,
thing.
I know what you're saying. No, points aplenty for everybody. Oh, there's my board back.
Yay.
Okay. And wait, so I said hello, Sylvie. Good to see you, Ashton. Good to see you, Ariana. Good to see your avatar. Good to see Kayla. And who have I not? Fatima, hello. Isabella, hello. Abigail, hello. Who have I not? I think that's everybody. Is that everybody? I think that's everybody. Okay. Um, um, okay. Is that everybody? And now Remy, okay, and I see Eugene. Remy. Okay. Um, um, so we have a lot to do today. I'm very much, I've been hearing from some of you. I appreciate all the work you're doing. I've been getting some feedback and some questions and stuff from some of you during the week, which is great. I'm glad to see you're alive during the week. And Professor Tally Mercedes is still thrilled with you. We're going to find out today, and for everything I've heard is great. We're going to we have a lot to do. Maybe no, I'm not going to say it. We have a lot to do, and my first priority, my first desire is to talk about the lab that you just did with her. We're going to do that in like 1 second. I think it got well. We'll find out. I talked to her a lot right before it. I didn't talk to her a lot right after it. So we're going to find out from you. One thing though that she did remind me: is this correct? Is this correct that you don't have lab for the next 2 weeks? Is that right? Like you don't have it on the 13th and you don't have it on the 20th, but instead you have it on the 21st. Is that correct? That's okay.
Yes,
Yes, you're
we're
right.
on a Monday schedule on the following Tuesday.
Okay. Okay. That's good to know. But okay. Thank you. But we do have lecture Wednesday the 15th, correct? Is that correct?
Yes.
Okay. So that's also good because that means we have some time to. So we're going to spend less time today than we did last time setting you up for the next lab. Like we will spend a little time on that, but we still have more time next Wednesday to do that too. So we're going to do a little bit more like straight up lecture material today. I mean, discussion material today. And let me say too, I really appreciate, I feel like you're a very discussion oriented group. And I think that's really helpful to you, to your education, and really helpful to me. Like, because this is so long on Zoom. I mean, the more we're all in it with each other, I dread this as much as I don't dread you guys, but Wednesday's a very long day for all of us. And it seems like it's going to be torture every time. And you guys have made it seem a lot less torturous to me by all your comments and participation. So I hope that's working for you too. Keep it up is all I'm saying. Okay. And with lecture, I'll say this too. If I'm worried about saying this. It's possible because lecture is a little bit different from lab. If we do get through everything today, especially since we do have this gap in labs, I mean, maybe we go a little bit early today. I didn't say that. You didn't hear me. And definitely Professor Talley did not hear me. I definitely didn't. But maybe I wouldn't be the worst thing if we could get out of here a little bit early. Maybe even if it's a choice between that and a break, maybe that will happen if we can. But I did not say that, and you did not hear me, and nobody is smiling. And oh, suddenly Kayla has a video with smiles. Amazing. That's no, I didn't say that either. Okay. So here's what I want to do. I'm actually going to turn off the board. We don't need the board for right now. I don't think we need it. I'm going to turn it off for right now. I want to, how do I do it? I want to have discussion. I know last week you had some motions in lab. I want to hear about that. And then and just like last, and I want to hear about this whole uncertainty thing that I know got introduced. I'm sure we need to process that, or at least I do a little bit. But before we even get to the uncertainty business, just as far as the motions, like the propositions, the equations, anybody start, like what equations do we think are true or are false as of the lab from last week?
We got the square root one as true.
Yes. Yes. Does everybody, I agree with that. To cut to the chase, I totally agree with that. And he says I'm assuming too, because you're a small group. I'm assuming you would let me know if you had I shouldn't jump the gun. Oh God, I shouldn't jump the gun. Is he speaking for the whole class? Like did you all, and I'm not talking about how good your results are, but is that, oh, Ashton's about to say something. Yeah, Ashton, go. Oh, no. Okay. But is that what you all, by the end of the class, you all agree with that? Not to jump the gun, but that maybe I should use the board. You're saying that that the period of a pendulum, oh, someone's here. Wait, someone's here. Where'd it go? Someone's here. I know someone's here. I felt it. No? Yes, she's back. Okay. You're saying that the period of a mass going back and forth on a spring is approximately proportional to the square root of the mass going back and forth on the spring. I'm taking that to mean that's what Remy's saying. That's what Ashton is nodding. And even though I shouldn't do this as a teacher, yes, to cut to the, I think that's right. So that's great. That's number one. And that does mean indeed that it's wrong to say that the period is proportional to the square of the mass. It's wrong to say that the period is proportional to the mass itself. It is right to say, if anything is right, if anything is close to right, it's that one. The t is proportional to the square root. Okay, cool. I want to hear more of the nuances and details of that in a second. But before I do, what about that fourth statement, which was independent of the others? The whole idea that the period, does the period relate to the initial displacement of the mass? What did we feel about that?
I don't really understand what you're trying to ask me.
Oh, okay. Fair enough. So, and maybe I might use the board again in a second, but I believe I gave you guys 4 statements to test. The top one was T directly proportional to M. Wait, sorry, someone's here. Hang on a second. Okay. The top one was T is directly proportional to M. Then the next one was T is directly proportional to M squared. Then the next one was T is directly proportional to M to the 1/2. And of those 3, you, Remy, just correctly told me that T is proportional to the M to the 1/2. I totally agree. But then there was a 4th statement that I said could be true or false, no matter what you found of the other 3. There was a 4th one that I believe, unless it didn't come up, but there was a 4th one where I said, oh, sorry. Okay.
Yeah, is that the subscript 0 one?
Right, exactly. Yes. Oh, yes, that's what I mean. And and I see in the direct chat, we should turn this into a game show. So someone in the direct chat is saying that 4th statement is not true. I'm not saying names because it's direct chat. The names have been changed to protect the innocent. But someone in the direct chat, but yes, that 4th statement, the statement was, maybe I should use the board. The statement was period directly proportional to X naught or Y naught, meaning is the period of the pendulum directly proportional to the initial displacement of the mass. And at least one person in the direct chat is saying, no, it was not the case that T was directly proportional to the initial displacement. Is that what the rest of you agree with that? And the direct chat person total credit, total point. I mean, I don't know if the fact that your classmates are agreeing with you makes you more comfortable coming out in public, maybe, but you're totally right, direct that person. But now I'm going to push it a little bit further. So that's good. I agree. I'm sorry. I agree. The 4 statement is not true. I do agree with everybody so far that out of the 4 statements, only one literally was true, even though more than one could have been, but only one is. I'm going to push a little further now. Maybe I really should. I'm debating about the board, but let me push. I just feel like things get weird with the board sometimes. I'm pushing a little bit further with that 4th one. I want to get the 4th one. Yeah. With the 4th one, I agree with you guys that the period is not directly proportional to X naught. I agree. That means it's not directly proportional. It means that you don't get some sort of diagonal line on a graph. It could mean, so to say that it's false, could mean that you get like a curve on the graph. When I say the graph, I mean if you put X naught on this axis and you put T on that axis, if you're saying it's not directly proportional, you're saying it's not like a diagonal line, which I agree. But then what that means to me is, okay, so it could be like a curve, or it could be like a curve, like it could be a square root thing, or it could be something else. Like what did you find, or did you, like what if anything is the relationship between T and X naught, or is there not one, or what did you find about T and X naught, if anything?
On our graph, it looks like flat, linear, horizontally.
It does. Okay. First of all, let me say to everybody, and I'm going to start using the board. We already have more ideas here collected than I'm going to start writing this down. But I'm excited. Can you tell? I'm excited. I need a Bitmoji for this. Like, first of all, what Remy just said. Oh, and people are even laughing too. This is great. We can do this all day. We can make it a 4-hour class, no problem. My son would kill me. Okay, first of all, what Remy just said, let me make clear. The first thing about what Remy just said is it made it clear that he understood the question. Like that totally made me feel like a human being. Like what he just described what the graph actually did look like between T and X naught. So frankly, any description he gave, I would have felt like, good, we're in a conversation here. He's totally on point with the question. But in fact, further than that, what he said was, I believe Remy said that his graph, if you put T on the y-axis and you put X naught on the x-axis, he said he got more or less a horizontal line. And yes, I think that's correct. Now we're going to, of course, a big part of today, we have to get into exactly how correct is correct and all that. But on the basic level, like we are all on the same page here. Like that is what I would expect. I'm actually excited. And I mean, don't forget, I'm doubly excited because even if this were just like straight homework or lecture stuff, like y'all are getting right answers and that's satisfying. Like we seem to be knowing the same science, but also like it is a lab. So we all know it's very possible to understand what's going on and still not get particularly great results. And I know that no one's results, I mean, I hope no one's results are perfect. But if you're telling me that you got results that were adequate enough to come to these descriptions and conclusions that you all are saying so far, I'm saying something correct is happening here. So I'm gonna pause for a second. I want to introduce the board because I think we already have 2 conclusions on the table, and I want to probe them more deeply now. Like we're going in layers. What you're telling me so far is T is directly proportional. Well, excuse me. You're telling me that period is a linear function of X. I'm going to start again, and I'm definitely going to use the board. So far, you're telling me that period of an oscillating spring is directly proportional to the square root of the mass oscillating on that spring. Okay, so that's one thing. The T is directly proportional to m to the 1/2. And you're telling me, so it's a linear function of m to the 1/2. And you're telling me that the period is a constant function of X naught, of initial displacement of mass. That is 2 big statements. You're telling me this kind of function and this kind of function we can use to describe a mass oscillating on a spring. That's a lot already right there.
And then it also, and everything comes to where you're at. Yes, and look at that. That's how it works. You don't go to-
Okay.
Exactly, so you come to us, and
Okay, I'm gonna send him. Okay, thank you. All right. No offense. Some of our best friends go to John J. Hold on. I'm just setting up the board so we can summarize this so far. Hold on 1 second. Okay. Okay. Here comes the board. We're gonna start taking notes now. By the way, why does it say this just on the board? Like that looks silly. Like for sure. What am I saying? Just so you understand, like the title SHO stands for this larger topic that we are now getting ourselves immersed in. The larger topic that we're getting immersed in here, the first real big topic of Physics 102 is SHO stands for simple harmonic oscillation. That is what we're looking at from a lot of different perspectives and a lot of different angles here all at once, like lecture homework, lab experiments, discussions. But what we're trying to we have a lot of different equations going on. We're trying to bring these pieces together. But the topic that we're looking at here, just so you know, and we'll be on it for a little while, for like a couple more weeks, like 1 or 2 more weeks. The topic here, if you ever wanted to look it up on the web or something, is simple harmonic oscillation. And I'm going to define that more specifically in a moment or soon. Oscillation, of course, well, I should say, of course, oscillation means periodic or repeated or cyclical motion. Oscillation is motion back and forth, like you're studying in the lab. It doesn't always have to be literally back and forth. Like a pendulum, which we might look at next, a pendulum oscillates in a curve back and forth, or fans, like desk fans, room fans oscillate back and forth in this sort of curvy motion. But to oscillate means to cycle, to engage in some sort of periodic or repeated pattern of motion. That's what oscillation means. What we're studying here is a specific type of oscillation called harmonic oscillation. It's a specific, very steady, very regular, very predictable case of oscillation. And by the end of this class, I have to give you a much more rigorous, precise definition of exactly what we mean by harmonic. But I'm not going to do that yet. I'm just saying in general, this chapter that we're in is simple harmonic oscillation. And the two things that we're saying about it so far, it seems,
What's the third row word?
Sorry, good question.
It's-
Good question. Sorry, asserting is what I'm trying to say. You're right. That looks like, sorry, asserting.
And what's the last word?
Right, the one I just erased. Yeah, that was bad. Well, the one I just wait. It was just sorry. 1 second.
Yeah, the one you just.
Okay, all right. So I'm erasing because you're right. It was illegible and it was the wrong word anyway. The period. Okay. Okay, I'll just read this out loud. I'm going to start getting mathematical here. So far, we are asserting when a mass oscillates, so engages in cyclical, periodic, repeated motion back and forth on a Hooke's law spring, meaning a spring that obeys Hooke's law, a spring that is reasonably well behaved. When a mass oscillates back and forth on a Hooke's law spring, the period of oscillation is defined to be the amount of time measured in seconds for one cycle. You might even want to add the word full. I mean, I ran out of room here. You might want to add the word, you might want to say for one full cycle, just to emphasize. In other words, period, and I know you know this. I'm just like reviewing where we are so far. I mean, clearly you know this, otherwise you couldn't have done the lab, but period means amount of time for a full cycle, like a round trip, a full there and back. That's what we mean by period, right? And it's designated with a capital T, right? All of this you know so far. I'm just refreshing where we are. But what we're asserting now about this, I'm going to turn the page. Tell me if I should turn back. I think I put some participation things in there about turning back and turning forward, but what we're asserting, what you guys are telling me so far is that just happened. Okay. Yeah, in fact, actually, we'll do it like this. Okay. This is what we are saying so far, right? I mean, you hopefully I just wrote maybe in symbols that so the top where I wrote T is F parentheses square root of M. That's a way of saying T is a function of the square root of M. Specifically, it's a linear function of it, but T is a function, period is a function of the square root of M, and T is a constant function of X naught, i.e. in English, again, hopefully I'm just saying different words, something that you already all are telling me and you all found out last week. The period of oscillation, sorry. You're telling me that when you have a mass oscillating back and forth on a spring, you're telling me that the period of oscillation depends linearly on the square root of the mass, and yet it does not depend on the mass's initial displacement. I'm just summarizing what you're telling me so far. Now I really do want to get into and I'm impressed that you found this. I definitely want to get into the discussion of how you found it, when you found it, how hard it was to find it, how much you believed it, how good your results were, the uncertainty. I want to get into all, I mean, I definitely want to get into all that. But first I want to put this into some lecture conclusions or into some more, I want to do something with this scientifically. Okay, I want to dwell on this for a couple minutes. And again, I do want to turn this back into a discussion of really what went on last time. But since you seem to have these very confident, like important conclusions, I want to just expand on these conclusions for a couple of minutes first. You're saying to me, and I'm not tricking you, like you're correct. Like you're telling me that you found that the mass does somehow depend, excuse me, the period of oscillation does somehow depend on how much mass you put on the spring, but it doesn't depend on where you brought the mass when you started off the oscillations. Now, both of those, for a given system, once you set up your mass going back and forth, how much mass you put on the spring and where you put the spring, those are both constants. Those are both constants for one particular trial of the experiment, for one particular operation that you do, for one particular data collection procedure that you do. The mass doesn't change throughout its 20 oscillations, and the initial spot that you put it to doesn't change throughout the 20 oscillations. I mean, granted, wherever it is at any moment certainly changes, but the designated initial spot, how far you stretch the thing to start off with, that's a number that never changes throughout the oscillations. So both of these, M and X naught, they're both constants. They're not variables. They're both constants. But I want to bring your attention to the fact that they are different type of constants. And one seems to be having one kind of impact on the experiment, and the other has a different impact. There's names for these different types of constants. So I'm going to turn the page. Tell me if you want me to go back, but I'm saying.
What's the word after system and before configuration?
Good question.
Oh, ingredients. Thank you. Sorry, ingredients. Yeah, sorry. Okay. Just like there are different I mean, most experiments have two or more different variables going on. There's independent variables and there's dependent variables, right? Well, there's also different types of constants. one major distinction between constants is that a parameter is one type of constant. A parameter is a physical description of the ingredients of the equipment, the things, the objects that you're using in your experiment. And those measurable properties, those numbers, those characteristics are numbers that go into our equations and all that. And they don't change throughout the data collection procedure. And they don't change because you don't change your ingredients in the middle of your data collection procedure. But there's also how you set up your ingredients, how you configure them. And configuration is like a choice that you make even once you've already fixed your ingredients, even once you're already even once you've already chosen your ingredients, now how you put them together is up to the user. It's a configuration. And often, especially in physics, we'll call the way that we put the things together, specifically, for example, here, how far we hold the mass out when we start it vibrating, we'll call that an initial condition. Specifically, in this case, the initial position of the mass. Now, these are two. So the first thing is called a parameter. The second kind of constant is called a configuration or an initial condition. Now, apparently, your oscillation depends on one of the. Oh, I just lost. Oh, no. Okay. Hold on. I'm going to have to pause in a second because I just. Sorry. But apparently, your oscillation time depended on one of these, but not the other. And it's actually a rather big deal that it didn't depend on the other. The fact,
Sorry. One more question. Oscillation for what time?
well, it says, it says for which time. No, I like your questions. And it's actually forcing me to be more careful about this. It says oscillation for which time, but you know what? That's really awkward. I apologize. Scratch that. You're right. This is totally awkward the way I'm saying it. Hold on. My apologies. It said which, but you're right to not be able to read that word because it didn't make sense to say that. Let me start. I'm going to start this again. My apologies. And then we're going to pause anyway, but hold on. Okay, my big point for the moment, and it actually is a really big point, is this thing that so you're watching a mass go back and forth oscillating on a spring. There's all kinds of ways to oscillate. I could walk back and forth in front of this Zoom camera right now, whatever. I could walk back and forth, do laps in my living room, and that would be called oscillation. But it would just be called oscillation. There's all kinds of ways that I could walk back and forth, and they would just be random or unsteady or uninteresting oscillation. When we observe an oscillation for which the time is independent of the space, and I'm going to say that a million different ways, but when we observe an oscillation for which the amount of time it takes to go back and forth to do a full cycle seems to have nothing to do with how big we made the cycle, we call that harmonic. And this is what you guys are telling me. And it actually is a very big deal. Like, let's back up for a second. And again, I will shut up soon and I will turn it back to you for 1,000 different dimensions of this. But I just want to or I just want to emphasize, it just seems like a mathy thing, like you, or at least Remy, and I think other people. Oh no, it wasn't just Remy. It was a direct chat person. I won't mention him or her by name, but a number of people told me, like, okay, when we tried out different initial displacements of this mass on the spring, when we pulled the mass to here and let it go back and forth, and then we pulled it to here and then we let it go back and forth, and then we pulled it to here and let it go back and forth, we found that at least approximately, at least reasonably, we found that no matter where we pulled the mass to, the amount of time it took to go back and forth stayed basically the same. What you're telling me is that the period of oscillation, it depended on stuff, like we could affect it, we could tweak it, but it didn't seem to depend on configuration or on initial condition of the system. Let me put it like, it might have depended on what you put in the system. If you put heavier masses in, you got different periods. Like, that's what you're telling me. But once you picked your ingredients, once you put a certain mass on this certain spring, apparently, no matter what you did to the mass within reason, no matter how far you extended it initially, you're telling me that it still vibrated, oscillated back and forth at roughly the same rate, in roughly the same amount of time each time. You're telling me that the time for each cycle did not depend on how big in space each cycle was. First of all, if anything else I'm saying that particular type of oscillation, when the period is so constant that it doesn't even depend, when the period of time is so constant that it doesn't even depend on the amount of space that we give the oscillation, that's called harmonic. That is a very special type of oscillation. And I'm going to say it one last time, and I'm going to pause. I'm saying it two ways. I'm saying, number one, you're telling me that the period did depend on parameters. That you are telling me that. You're telling me that you could vary the period of oscillation by varying the ingredients in your experiment. The period was determined by parameters of this system. But you're also telling me that it was only, in effect, based on what we've measured or looked at, you're telling me that it was only determined by parameters. It was not determined by configuration or initial condition. You're telling me that you found a period of oscillation that was independent of configuration, independent of setup, right? And specifically, I'm going to say it one more time because it really is actually a crazy idea. Hopefully you're going to see more and more as we talk about and see other examples. It's kind of a crazy idea, but you're telling me that the time of cycling did not depend on the size of cycling, that you could make bigger cycles or smaller cycles in space, and yet they would still yield the same amount of time for each cycle. And I'm not disagreeing with you, I'm like excitedly agreeing with you, but that type of oscillation is so steady, it's so constant that apparently it can't even be affected by the size. That is called harmonic oscillation. That's what we're studying here. That's like our first statement about harmonic oscillation is that harmonic oscillation is when the period is independent of the initial condition. In fact, I'm going to throw one more word in here, just because we're doing vocabulary in a way, just one more word. I'm sure you're familiar with this word. Okay, and slightly more technical language, and then we're going to move back. That promise. I'm like going to I'm putting down the gun, I'm putting down the cannoli, the pen. I'm going to turn it back to discussion with you, but just to put more piece of technical language to this, we're saying ultimately, so oscillation just means periodic, repeated, cyclical motion, but harmonic oscillation means oscillation for which the period is independent of the amplitude. And I know you've heard the word amplitude before, but what am I saying amplitude is in a physics context? Amplitude. The amplitude is the word we use for the initial displacement from equilibrium, like again, x naught in this case, the initial displacement of equilibrium. And we call it amplitude in recognition of the fact that if you pull something out from equilibrium and hold it there and then let it go, that initial displacement is going to become the maximum displacement. We're going to see that in the homework when we start going over it finally. The initial displacement and the maximum displacement are interchangeable. They're one and the same. So to capture that whole idea of initial or maximum displacement for equilibrium, the farthest that the thing ever gets from the center, we call that the amplitude. And so the amplitude is like the size of the oscillation. The amplitude is the size in space of the oscillation. And what we're saying here is that there's a kind of oscillation known as harmonic, where apparently the time of the oscillation doesn't care about the space or the size of the oscillation. And I keep saying that over and over, because honestly, I'm going to shut up now. I keep promising that and I keep breaking my promise. I'm going to shut up and I'm not going to shut up, but I'm going to turn it to you. But the reason I keep saying this thing, I keep saying it because hopefully on the one end, you're getting it. You might have already gotten it before I ever said it. Hopefully you're hearing me say it and hearing the truth. But if I say it enough times, to be super honest, I'm also just trying to throw you a little bit, because if I say it enough times, I'm hoping that at various points, each of you half consciously will start realizing that what I'm saying actually doesn't sound like it makes sense. Like, okay, it makes sense. I'm saying what you found is the time of oscillation doesn't depend on the size of oscillation. That's what you found. That's what you found. Doesn't matter where you bring the mass back, you're still going to get the same number of times over and over of cycles. But if I keep saying it in these simple, straightforward terms, the time of oscillation, the time for a full cycle does not depend on the size of the cycle. Like if I say that enough times, when I'm not asking for an argument and I'm not trying to trick you, but if you hear me say it enough times, I'm kind of hoping at some point, some of you will start increasingly to realize, like, that's a little weird. Like, that's a little weird. It may sound obvious because apparently you just found it to be true in the lab. But if we hadn't done a lab and I just walked up to you on the street and which would already be weird, and I said to you, like, look, here we go. We're going to like pull down this spring and it's going to go back and forth and back and forth. And I'm going to time how much time it takes to go back and forth. If I just said to you, if you want to take, if I said to you, I want to take a really, really long time to go back and forth, what do you think I should do? I would imagine that many of us would say to me, well, pull it down really far. Like if you wanted to take a really long time to go back and forth, make it undergo a really far space, like if I would think if you want this thing to take a lot of time, give it a lot of space or something like that. Or I would think if I force it to travel a lot of space, I would think that would somehow make it take a lot of time or something. But apparently we're saying no matter what space you give it, it takes the same amount of time. If nothing else, I'm trying to say that is kind of interesting. That kind of interesting thing is called harmonic oscillation. Now I'm going to shut up because I keep promising I'm going to shut up. I'm going to, I want to hear, well, first of all, okay. So first of all, is what I'm saying so far at all makes sense? Like, are you with me so far? Are we, thank you, Sylvia. I totally saw that. Thank you. That's all. And thank you, Ashton. Okay. I'm not going to say it. I'm not going to say it. Okay. Thank you. Oh, and thank you, Catherine. Oh, that's thank you, Salady. Thank you, Jonathan. Oh, it's like totally a class. That's all. Thank you, Salady, Catherine. Oh, and Marina. Wait, why does it say Marina, but it doesn't? Okay. But thank you. All right. So you're with me. Cool. I'm going to get rid of my screen for a second so we can really get together. We're like, we can cozy up with Marina's cute dog, sort of, and a cup of tea. I'm going to get rid of the screen because now I want to hear it. So that's our conclusion so far, is that harmonic oscillation is oscillation for which the period of oscillation is independent of the amplitude of oscillation. That's like our big finding so far. We want to relate this back to the homework. We want to relate it back to equations soon. I want to give you some new equations that you don't have, some new math that you don't have yet. Believe me, that's all going to happen. But first, I want to get rid of this board and I want to hear some specifics about this lab. Like I am. So wait, save. Is it saving? And remember, now that we're starting to take notes in this class and stuff, remember, whenever I take notes on this screen, the PDF goes to you to Google Classroom right when we're done, and the video goes to you too. You should still take notes, honestly, but like you will get all that. Hold on, I'm just leaving. Okay. But now, so I guess I want to hear, well, first of all, does anybody want to show? I was really excited last time that you showed graphs last time. Does anybody, maybe somebody new, maybe someone who didn't last time? I mean, if you put it in the screenshot, but I never used it last time. I'm not screenshot. I mean, if you put an image in the chat, but I didn't explicitly use it, then I definitely want to encourage you. Those people who put something in, but I never dealt with it, definitely an invitation to them to share something today. But people in general, I guess what I'm really saying is I was so psyched. I spent so long on Jake's graph last time and I loved it. But I want to make sure some other people get a chance to, so sort of politely, with total respect. Anyway, so not Jake's for the moment, but does someone else want to show? I know at least one of you, I don't remember if it was Eugene, at least one of you put a graph in the chat that I never dealt with. That was Eugene. All right, Eugene, do you want to, oh, Dr. Pepper. I love Dr. Pepper. Okay, sorry. Okay. I mean, any soda with a PhD. I mean, how could I not? Okay. But yeah, do you want to go for it if you've got a graph to show? Okay.
We did actually discuss about the 0 point. And then in lab, we actually spoke to Mercedes and she did agree. So we checked with her. So for this time, what we have so far, I'll just screenshot it and show it to you.
Cool.
But so we did few graphs, but I think this is the most linear one.
Okay.
Okay.
Oh, cool. Okay, share the file meeting. Oh, cool. Right. Okay, so I can. And you guys, wait. I don't mean to not give you screen sharing privileges. I mean, you can. Okay, I see. Wait, do you want to just screen share that? I mean, I can do it, but oh wow, look at that.
Could I tell you
Honestly,
something
don't know how to do the screen sharing.
Oh,
That's why I
okay,
keep
okay,
sharing there.
okay. That's fine.
about that graph? I just want to like, because we did have one point. Which point was it? Yeah, the 12 and the 3, point. Which one was it? I'm gonna forget. One point, it was the 12 and the 10. 10, for some reason, our data gave us a higher point than the one for 12. It was 0.032 higher, so it's not technically linear, but compared to our other graphs, it was much better than, our other ones.
Okay, no, I think I understand what you're saying. Hey, wait a minute. Wait, I might ask you to repeat that, but no, and I totally appreciate that. I think I understand. Actually, no. Let me ask you to repeat. I got most of it, but I got distracted by something. I was looking at the graph. Something else excited me about the graph. But say, all right, tell me. I'm sorry, Ashton. Say that again.
It's fine. It's been, my brain's like broken. But so for the point, the 12, the point with X12 and the Y of 30,
Okay.
our 10, our point 10 obviously is 0.532. So technically our higher X value has a lower Y, a point of 0.032 lower. So like it's not technically linear, but when we were doing this, for some reason, that's just what we got in our data when we divided by 20 and everything. So, but this graph compared to like every other graph we had was the most linear, because it was the only one that kind of went mostly straight up, except for that one point. That's what I just want to clarify.
Yeah.
Okay. No.
Compared to other graphs that we did on the same day, basically.
Okay.
This one was the most.
Okay. No, this is very helpful. Many things I want to say about this. Both of you. I mean, all of you, but like, so first of all, when you said compared to the other graphs of that day, you mean like the other choices that I get. Like, you don't mean other graphs of this exact, you mean like the other choices that
the other choices.
Okay. So first of all, you guys are, if I understand this correctly, you are honestly telling me, and I hope, and I really mean honest, like I hope the minute we all get terrible data or we don't believe our data, we don't like it, I hope we all trust that our grades are not going to be dependent on that. Like, we really are here to be scientific. So I'm trusting you that you're trusting me, blah, 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 blah. So you're telling me that honestly, even though you didn't think this graph was perfect and you actually have some issues and concerns with at least one of the points, you could even tell with your eyeballs, you're all saying that it was blatantly, if anything was going to be good, it was this one, and the other ones were not even close. Like, it was an eyeball easy distinction to make. That's what you are saying? Okay,
Yeah.
that's really helpful. I mean, because that's what we're looking for. Like, I mean, part of why people really get messed up in science is they really get, not you guys, but I'm saying part of what I'm here to do is like remind us all continually that it's not just that sometimes we're allowed to be imperfect, kind of, sort of, in the lab. It's that fundamentally it has to be imperfect in the lab. Like, we think we're sort of being like, it's like not teacher charity, that when we say like, you could expect there to be some yuckiness in the lab. What we're saying is like, it has to be the case. If we ever see perfection in the lab, somebody's lying. Like, somebody is going to academic jail. Like, it has to be imperfect, right? For real, right? So I we don't have to apologize for imperfection. In fact, we trust imperfection more than anything else. What we want, though, and this all is circling back to like the Jake thing from last week, like a lot of it is, what we want to recognize that things are going to be imperfect, but we want a way of comparing how imperfect is imperfect. Like, how good does something have to be to accept it, or how imperfect does something have to be to reject it? That's the real art of the science. And it starts always with comparison. Like, I'm going to ask in a second, In fact, wait, can I share more than one screen? Wait a minute. I'm going to try in a minute. Because the first thing I want to say is like, just like you guys, if I looked at this data, I mean, I understand why Ashton is quickly like qualifying one of the points and explaining a context for one of the points and all that. And if I looked at this data and I was saying like, is this a straight line or not? Just like you, if I just look at it, it looks pretty straight, but I don't really know whether I would really call it straight or not. The first thing that really always goes through my mind as a scientist is compared to what? And the first thing in this, the way we do these labs is, the first thing is, well, compared to the other choices, let's start with that. And if you think, even if you're like fuzzy on this, but it's blatantly less fuzzy than the other choices, we're getting somewhere for sure. In fact, so I even want to ask before I go any further, I don't know if I can simultaneously share two, but does anybody else have the guts or the willingness, and maybe somebody new, can someone show me one of the seemingly bad graphs so we can see this comparison? And does everybody understand that bad is good here, right? Like if two of the graphs were like super bad and this one was only kind of bad, that's a good thing. Like it doesn't mean they're bad. It means they're showing us information. But so I don't know if anybody else has one of the other ones or no, or maybe. Is that because I'm sharing this? Wait, changing. I don't. What's going on? I see. Hold on. Well, all right. I'm gonna keep. If anybody else has one of the other graphs to share, let me know because I'd be very interested. I mean, obviously, I'll see them from Mercedes at some point, but okay. But there's other comparisons we have to be until I see those. Yeah, I would also agree. Oh, okay, 0, 0.
So basically, we're saying that if you look at the fourth dot, it's lower than the third one. If we measured it correctly, it should be a bit higher than the third one because we would expect to like increase.
Yeah, I mean, I do agree. Okay, I have to be really sure. I agree. You're right. If any of those dots is more particularly funny than the other ones, it is that one. But again, I really have to tell you, how can I put this? If that dot weren't there, I mean, that has to have. Okay, this gets us into uncertainty. Like there is definitely a trend line, a straight trend line that would capture this data, even with, or especially because of that dot being sort of there. Like, let me put it another way. Hold on, let me back up. Because I do like this data, and I do like the fact you're calling it straight, and I do agree. And sidebar, something else I'm noticing about this graph that got me distracted in a good way a moment ago. Something else I'm noticing about this graph is, hello, this graph was done on Desmos. I'm totally noticing that. I'm totally excited about that. That's a big breakthrough. And I'm guessing, and I'm very excited. So that means some of you are starting to at least try to use Desmos good. Now, I'm also guessing that maybe it's the fact that you did it on Desmos that you left it as a scatter plot. I'm guessing that because you did it on Desmos, you're not yet comfortable on how to get a trend line for it. And if that's the case, that's totally fine too, because that's what I want to show you today. Like once I show you, like it's not obvious how, but once I show you how, I think you'll see like how much more fun or interesting it is than it is to do on Excel. So I'm glad. So yay, you guys for trying Desmos. Hold on. Oh, and you have, oh, that's it. I just got called sir. What? Oh, okay, cool. Okay, no, way to go, Ashton. First of all, seriously, and way to go, direct chat person, for staying with me and honestly admitting. Okay, so does that mean? So did other people like direct chat person who just told me something? Do you all, besides Ashton, do you sort of feel comfortable at least getting this far on Desmos now? Like, I totally understand that you don't know how to make a line yet. I'll show you that, hopefully today. But does this mean, like, direct chat person, are you saying that you could do that much on Desmos now? Am I making sense? Hold on. Oh, you did. Okay. So some of you are using Desmos and some not. Okay. Oh, okay. Oh, okay, wait, a lot of things happening in the direct chat. Wait, and by the way, I didn't mean to like make a personal thing about Jake last time, but I mean, it was great what Jake did, but it was Jake the person. Like even if, okay, so different people are using different things. Okay, well, I want to get you all to Desmos. That might end up being a goal of today. I want to move us to Desmos for precisely the very reason that you don't know how to make a line yet on Desmos. Right, is because it's a little bit of a funkier thing. But once you know how to do it, it reveals so much that can't be revealed on Excel. So I want to get you there. But also, let me just say, yes, I loved that Jake and others shared last time. But if you happen to be in Jake's group, that doesn't exclude you from sharing today. I mean, I don't care that you have the same graph as Jake. I'm not saying that now anything that Jake ever touched like is banned from this class or something like that. I'm just saying that like that Jake got to talk and stuff like that. So someone else, even if you're in Jake's group, like you could show your data. And I'm not saying you get my point. But wait, no. Yeah, okay. Oh my God, I'm so sorry. Okay. I'm gonna stop. I mean, anybody whose name rhymes with no, and I hope I see I can't see your faces either. This is the danger because I'm on the screen share thing. Oh, and no. Yeah, no, it was awesome that Jake did that. And look, okay, I'm gonna shut up. I hope it's clear that I'm happy. Okay. I want to show you Desmos. I'm not gonna do it yet. One thing I want to say though. I think this data is good. We have this ongoing theme in this class that is a big theme in this class, and it's going to continue to be a big objective of this class. Like one of the main things we are going to try to learn by the end, and it is a process. And when I say learn, I don't just mean in a casual way. I mean, like it's going to be part of your labs. It will be whenever we have an exam to be part of that. One of the main things we're trying to learn here is like the answer or the technique to address the super legitimate question that many of you posed last time. Many of you, some of whose names might or might not rhyme with rake, that you pose this question of like, how do we know? Like, how do we actually know whether something is good enough or not good enough? If we're assuming that everything is always imperfect and everything you can always sort of say, that's kind of okay. How do we know whether to accept things or not if we literally don't know the answer in advance? That is such a real question. Like literally, if I could teach you nothing else besides at least how to engage in that question, I'd be happy to, because that is the art of the real science. That's where science is real. And the first thing I want to say to you about that, the first thing I want to say to you right now is when you guys are apologizing for that one dot, I mean, when you're explaining that one dot, yes, I understand you're being super honest and super, all this intellectual integrity, trying to explain why that one dot is bad. But, if you really take a step back and you really accept the idea that no data in a lab could be perfect, that no data point, no point of information in a lab could ever be perfect. And the reason we take tons and tons of measurements is to, over time, compensate for the imperfect, to average out and smooth out the imperfection that each one is contributing to the whole. Then if you really think about it, for any of us to ever apologize or explain one dot out of 5 means we're actually assuming that the other 4 dots are better than that one. And that's an assumption. Like we don't know for a fact, each of those dots, it could be the case that that's your best dot, honestly. I mean, is it likely? No, it's less likely because there's 4 others, but it's only 4. It's not a huge amount of data. There's nothing, in other words, it's not that one point is wrong and the others are right. It's that one point reminds us that none of those points is to be taken too seriously. Each of those points should only be taken sort of seriously, not perfectly seriously, but also not unseriously at all. There's a middle ground of how seriously we take all this, and that middle ground comes from uncertainty analysis, and that's what we have to get into next. Hold on. Okay, wait, I'm going to pause for a second because I do feel like there's noise in the background. Is there someone who should be muted? Or maybe they're muted. Okay, they're muted. Okay. I think that, okay, let me see if, I think, okay, it's 5:40. It's 5:40. I mean, there's many directions we can go with this for a second. I have a lot more to say, obviously, and I have a lot more to hear from you. Oh, wait, here's a concrete question. Okay, I'm going to get rid of this graph for a second. I do want to go back to this graph. I'm going to stop sharing for a second, just because it's getting confusing on my screen. One question that, and I want to see more graphs before the end of this period, even if they're identical. I mean, it just helps me to see what work people are doing. But on this one, let me ask you honestly, because so far I'm still thinking the data is much better than I think you're thinking it. I think it's very convincing. On this lab, did you know tell me honestly, like, did you already know the answer from the start of what you thought you were trying to get? You could be honest. I mean, please be honest. Oh, wait, I think okay, I'm seeing the chat, but also Eugen is talking, but she's on mute. Wait, do you want to? Oh, well, a lot in the chat. Thank you, people in the chat.
Okay.
Okay.
So when we first started, we actually had no idea which one would be the right one. So we actually had to try each one of them. And then we compare all the graphs. They found out the one that we just showed you is the most linear looking graph. So we chose to just, share that today.
Okay, so that's really okay. Thank you. That's convincing. So I mean, that's persuasive. That's Eugen. And then I totally see, just to be clear, I see in the chat, like, after all the, so Jake is saying no also in the chat. Kayla is also saying no in the chat. Giselle is saying no in the chat. Thank you. And all of you that are putting things in the chat, remember, you can submit all these things for participation points in the portals. I hope that's clear. Jonathan, thank you. You're saying nope also. And then, and then Giselle is even getting more specific and saying that she actually did have a hypothesis or a prediction, which I should probably. Marina, thank you. And maybe sometimes I should ask, like, for you to make a prediction before you even. So Giselle's even saying she even thought she did know the answer, or she had a guess, and it wasn't even right. Oh wait, and there's more. Now there's Jake. Okay, let me see. So Jake. Oh, now we're really getting somewhere. And let me just ask, I mean, all of this is really, see, I could do this all day. I'm sorry, well, as you can tell, but I really feel like, and again, I always feel like I have to apologize to the people that, maybe this is not what you expect a science class to be, but I really feel like for me, this is what I need at least one science class to be, is just like actually sitting around and processing like what actually happened and what it means. I just feel like there's just not a lot of time to do that so anyway, I hope you don't mind. But so, and like, of course, I know the right answers, so to speak, but I don't know. Yeah, I mean, you're telling me a lot that I don't know. So wait, I've got to ask one thing: is Giselle in the same group? I'm just curious. Is Giselle in the same group as Jake? Oh wait. Oh no, it looks like no. Wow. Okay. Wait, can anybody I'm just curious because Giselle and Jake are both saying, well, first of all, okay, let me back up. I love the fact that you're telling me that many of you are telling me that you actually believed one thing, but then when you added 0,0, that meant another thing. That's great because that's really important. And that is one of the lessons of all this. That's definitely a scientific technique that's very meaningful. So that's cool. So like 3 of you were telling me that. And then also, your group, okay, it was Remy, Dewan, and I'm sorry, also someone tell me at some point, Dewan, do I say Dewan or do I say Dewan? Or I mean, can you I've had that name before, but I always make it wrong. Okay, well, all right. So Giselle is with Jonathan, Sylvie, and Marina. Jake is with Remy, Dewan, and Kat. Oh, really? Okay, thank you. Okay, you sure? Okay, cool. Thank you. Okay, so this is great. And the only reason I'm asking about the lab groups, like in a way, it's not my business, but I don't know what that means. But so that means there really was this common theme. And again, all this is based on honesty. Like, but I'm assuming I don't know why anybody would lie about this. And so yeah, you're telling me. So you see, this means that science is really happening. Like really, really. If you guys. I'm not saying that science is democracy. I'm not saying that. But I'm saying you all went in and you all go in, you don't know an answer. You don't know which something is. You do a bunch of stuff and none of it is perfect. And you're groping around in the dark and you don't even have a sense of perfect direction. You grope around in the dark, you do stuff, Then you even do some wrong stuff, but then you adjust it with the community and you look at what the community is doing, you take that into account, and incorporating what you do into the community is very much like the human version of redoing a trial 3 times and then averaging it out, right? Like the whole idea is no individual point of data is perfect and no individual person is doing things perfectly. And a whole collection of data is not perfect, and a whole group does not perfectly know the answer. But the more trials we do, and the more people we're checking with, and the more we bounce back and forth, the more we're statistically just converging on increasingly reasonable or increasingly persuasive models of the truth. And by the way, that's all any of this is. All of it, even the formulas that you think you got from your chemistry teacher or something that were handed out from a textbook, they are the result of huge repetition, reproduction, collaboration, trial, community, and we eventually converge on what we think is our best model for the truth. I mean, it's always like that. So your lab is just a smaller version of that larger idea. But you're telling me that you went in groping around, not really being sure, even having a hypothesis that in some cases turned out like to be rejected. But then by the end, even here's the key point. It's about comparisons. In the end, even if you didn't think this graph was perfect, and you didn't think that graph was perfect, somehow the imperfection of this one was so much more blatantly, intuitively, noticeably large compared to this one, that you said, all right, it seems like, reasonably speaking, this is the deal, even despite my original expectations. That's how it works. That's still not a clear end of the story standard about perfection or imperfection. But one big aspect of how you know whether to reject or accept stuff is by comparison to the scale.
I
Okay,
have
sorry,
a question.
Yes, please go.
So,
Sorry.
for our group, I was with Sylvie, Jonathan, and Giselle. We initially thought motion 1 was true, and then based on 2 eventually being more linear than 1 after adding 0, 0, we thought that was true. But can one be more true than the other but both be true?
Oh, wait, that's a really good question. There might be 2 questions going on there. Okay, that's a great question. Can one possibility be more true than another, but yet both of them be true? Great question. In general, that can be the case. In general, that there could be more than one thing that are both true, but one is like more true than another. In general, that can be the case, yes. But, and again, it's a great question, but sometimes, like here in this lab, with those first 3 options I gave you, they are actually contradictions of each other. Like those 3 options, only one of them could actually be true, if any of them. Like it could have been the case that all of them were false. But of those first 3, if one of them was true or more true than the others, like blatantly more true than the others, then the other 2 would have to be false. Only because they're opposites. Like in other words, I mean, they're mutually exclusive cases. So how can I give another example of this? Like if the 2 to make it more extreme. Well, okay, so no, here's really the answer to your question. Like it could have been the case that the option that you found, that could have been very, very, very true. And then the last of all the 4, if I had literally written it differently, if my last equation had been, or last proposition had been, period is a constant function of amplitude, period is a horizontal line graph, if I'd said that one could have been true, and you're the one that you found could also have been true, and it could have been that one of them was much more blatantly, clearly true than the other. Like that could have been a case. Like and it may be. You might even have this right now. Like you guys got a line for the square root thing, and then for the x naught thing, you got essentially a horizontal line. I'm perfectly willing to believe that your horizontal line is a lot crappier than your diagonal. Like, I don't know, but I'm just guessing, or I'd be perfectly not upset if it were true. I could imagine that you could have had more arguments about your horizontal line than your diagonal line, maybe. And so your horizontal line could have seemed like not quite as clearly true as your diagonal line. And yet they could both be true. Yes. So yes, that can happen. But that's because those two were two different ideas. Like, those are just two independent, unconnected ideas. They're like, one is saying like this, I mean, one saying this period depend on mass, and the other one saying this period depend on amplitude. Those are, it could be the case that you depend on both. Like, that's just two separate ideas. But in the other options, the first three that I gave you, I'm literally asking, does period depend on mass this way, or does period depend on mass that way? Well, it either depends on it this way or it depends on it that way. It can't be both. It's like the extreme case that would be if I'd asked you to test, does the period get bigger as the mass gets bigger, or does the period get smaller as the mass gets smaller? It's got to be one or the other. It can't be both. So my larger, is long answer, I'm saying totally that could happen. What you're saying could happen. But in the case of this lab, it could only happen with like one of those three and the fourth one. It couldn't have happened with two of those three. Did that make any sense?
Yeah, it makes sense. Thank you for the clarification.
Okay, thank you. Good question. Good question. Okay, wait, I want to go on. Does anybody, I'm just curious, does anybody, I really would be curious. I'm in my heart, the one I'm amazed by, the one that's like the one that I'm making a big deal here in the lecture part of this, where I'm saying, I'm making a big deal of that horizontal line graph. I'm saying you get that horizontal line graph that T is independent of or is a constant function of X naught. You've shown that this is not only oscillation, but harmonic. Now that, frankly, I'm shocked. I would think the data for that, I didn't actually think, I mean, to be really honest, I didn't think you necessarily would see that. I think it's really hard to take enough data to take it really precisely to see that. And these springs are really short. I mean, you only could vary them. There's not that much variation you could subject these springs to. So I'm not challenging you at all. I'm not challenging you. But I'm saying if you had walked in and hadn't even found that at all, I would have not been shocked. You're telling me that apparently you got a horizontal line for that last one. I think that's awesome. But I would imagine it's not, I can't imagine it's a perfect horizontal line. So I would love to see it. If anybody wants to give me an example of that horizontal line, please do. Pause for a second. Oh, okay, great. Oh, yeah, okay, wait, hold on. I'm looking. I see this thing in the chat. Wait, sorry, hold on one sec. Yeah, wait. Okay, sorry, I'm looking in the chat and we'll do. Yeah, no, I'm always up for review. That's a fair question. Do you mean though of what we're saying so far, or you mean like before an exam? I mean, we're definitely not having an exam for a little while. Or you mean we definitely do review before we do. Oh yeah, okay. The homework. I do want to get to the homework. 9 is where we're going with all of this. 9 is going to take us a while to get. You notice I haven't assigned any new homework yet for a while. And I do want to get to the homework. Yes. I don't know that we're going to get to number 9 today. I could give you, that's super hard. And that's why people are getting full credit on this homework, even if they didn't get to number 9 yet, including you will get full, you, Remy. I want people to try, but 9 is going to take me a while. But yes, we could shift gears in a few moments and start going over the homework. That is not a bad idea at all. I will. There's one, in fact, I'll take that very seriously. But let me just like let me do a couple more quick things, and then we'll take a little break and shift gears. Hold on one second. Bear with me for a second, please. Actually, wait, it's 6 o'clock right now. You know what? Okay, it's 6 o'clock right now. We go to 7:10. I still wouldn't be, I don't know if I won't be averse to us going a little bit early, but I do need to get to certain things, so I still can't promise it. But let's take like a 7-minute break right now, everybody. I mean, I have to balance fluids, so to speak. Let's take a 7-minute break now, and I want to set something up to show you too. Take a 7-minute break. We'll start again in 7 minutes. And I will try to go as quickly as I can and get to the homework, and I'll try to get to more things. But yeah, bear with me first, or take a break for 7 minutes. Okay, I want to show you guys. So we will thank you for your patience and all this. Hello. Okay, we're back. I will, yes, we will shift gears and go back to the homework, but I want to show you something that I think will help. So here is, I'm going to share a screen. Okay, here is, I believe, can you see? So I put in your data. I've taken your data from your screen share. I've put your data into columns. I should really say, this is really, I'm going to call it S and T, S for square root of M. I believe the data you gave me, and well, first of all, can you see? Can you see on the screen?
Yes.
Oh, sorry. Yes. Okay. Thank you. And I just messed it up by doing that. Okay. And can you see all the? I can't even. Can you see all the data points? Like, can you see all?
Like I can see the X and Y values on the side and the points.
Great. Okay. Like all 6 green points you can see. In other words, yeah. On the graph, you could see 6 green points on the green dots on the.
Yes.
Okay, great. Okay, so all right, so this is Desmos. Oh, I should have started from the beginning. I'm sorry, I forgot that some of you. I want to show you all how to use Desmos pretty quickly because we're gonna. I should have started from the beginning. I forgot that. So all I did. All right. So I typed in So look at here's the URL. We'll just put this in the chat. That's the URL. So many windows open. I can't. I'm putting it in the chat, but it's exactly what it's just desmos.com. Where is my chat? Hold on. Well, okay, you can see you don't even have to write in calculator. There's the URL. You can see it. I think you can see it in my screen. You go to Desmos. To put those points in, all I did, Desmos opened up, it was just an empty set of axes. To put the data points in, I hit plus. And you see these choices. Stop me if you can't see this on your screen. But when you hit plus, just to start from scratch, you've got these 5 choices: expression, note, table, folder, image. So I went to table, okay? And it opens up like that. So you have a table. Stop if you can't see this, because I know some of you can do this and some of you can't. But what I really want to show you, the part that's not obvious, is how you put in a trend line or a trend curve or whatever. That's the cool part. So look, like it opens up a table when you hit plus and you pick table, right? And then you could right away change the names of your 2 values. Like I would have made it M and T, but actually it's not M and T in your case, right? It's not mass and period. It's square root of mass and period. So I just called it S as just to remind myself that it was a square root, whatever. Okay. And then I just punched in numbers, from your measurements, right? That's all I'm doing. I'm just punching it, right? So that's how you make a table, and it starts making dots on a graph automatically. Very nice, right? Right in real time. And this whole application, this whole web application is free and all that. Okay, so I've punched them in. Tell me if I'm going too fast, but I think you won't find that part difficult. You just hit plus table and you start punching in your values into a 2-column table, and you can rename the table if you want. And it gives you this choice here that is just saying, okay, it's a scatter plot and it's in green. That's all that this choice here means. But now here's the interesting part. Really, I think super interesting part. And I just want to make sure you can all see this. The interesting part is, okay, I've got these dots. I look at them and I'm like, I think they're pretty much in a straight line. Which means that the dots are pretty much falling in like a y equals mx plus b formation, right? And b looks like it's 0 because it looks like 0, 0 is a point. The y-intercept looks like it's 0. So I think this is some kind of like y equals mx kind of situation. What I don't know, what I'd want Desmos to tell me or Excel to tell me is what's the m, right? if I think this is a line, that these dots are falling in a line, what I don't know is what's the best fit line. What is the line that, not what is the line that connects all the dots. I don't want to play connect the dots, because I don't believe my data could possibly be perfect. I want a line that captures, on average, the most reasonable representation of these dots, which means I really want a line that goes above some of the dots and goes below some of the dots, and ideally an equal amount. Like there should be, like going back to this whole thing where Ashton and other people were explaining about this one seemingly bad data point. I'm just zooming in with 2 fingers, typical zoom. Yeah, I'm zooming in like that, and I'm using 3 fingers to shove it up, just so hopefully you can all see it better. I want a trend line that I don't think any one of those dots is perfect. Even the dot that we think like, oh God, it fell below the trend, I think it's bad. Well, there's going to be some dots that fall below the trend, and there's going to be some dots that fall above. Ideally, you find a trend that doesn't actually go through any of them, but that it has an equal number going above and below. How can you find what that line is? Desmos allows you to do it physically by feel. What I want to show you, the part that I think you don't know, and again, please, I can't see your faces right now because I'm looking at the screen that I'm sharing. So please put in the chat, or please use your voice to say if you don't know where I am or what I'm doing. But hopefully or if you can't see, hopefully you're seeing a fairly zoomed in graph with 6 dots on it, 6 green dots on it, one of which is at 0, 0, and the others which, are sort of falling into a line. Here's what I do. If I feel that they're in a straight line, but I don't know what that straight line is, that means I feel that they're in a y equals mx plus b, but I don't know what the m is, or I don't know what the best approximation of m is. I go to Desmos, I hit this plus again, where it says add item. And now this time I already have the data sitting there in the graph. I'm not going to add any new data to it. I'm going to add an expression. I'm going to try an expression. Can I just, oh wait, I see something in the chat. Hold on, what's in the chat? Oh, cool. Thank you, Eugene. Okay, cool. And in fact, so can you just do, some of you, I can see some of your boxes below. Can you just give me an electronic thumbs up if you're still with me, if you're still seeing what I'm doing? Because I'm about to show you something. Or give me a thumbs up if you can see that okay, Marina, thank you. And you can see that I'm about to add an expression, like you see the cursor on, like.
Yeah, it's a blue box.
Cool.
At the
Good, great. Because this is the part that I think is exciting. Whether you think it's exciting or not, it's definitely the part that's new to you. And frankly, maybe Mercedes hasn't done this before. I'm not sure. But what we're going to do now is I'm going to add an expression. I'm going to add an expression that's completely, it's its own expression, its own function. It doesn't have anything to do with the S or the T. It's just its own function, but it's going to plop this expression, this function, onto the same graph paper. Like I'm going to give it a new thing to put on the same graph paper that already has the green dots. So I'm going to give it a new expression like y equals mx. Now see what's happening. Watch what y equals m. I'm starting to type the equation for a line. It's in a totally different color. You see it's in black because as far as the computer is concerned, or as far as Desmos is concerned, it doesn't have anything to do with the green dots that I just put on. This is like a new idea, but I'm typing an expression for a line. I started saying y equals, so it knew that y would be the dependent variable. So it just started going. Then I said m, so it's starting to think. Well, it's starting to think that for a moment, it believes that m is my other variable. It actually, for the moment right now, thinks that m is like x. So it's giving me the line y equals x. It's literally right now, if you notice, it's giving me a line with a y-intercept of 0 and a slope of 1, right? Like if I just, let me make this simple. If I just go like that, it just gave me the line y equals x. Now that has nothing to do with my green dots yet. It's just giving me the line y equals x, but it's putting it on the same graph paper. That's very nice. And frankly, if I go like this, plus 5, see, there's like the line y equals x plus 5. That's a line with a slope of 1, but a y-intercept of 5, right? But now here's the cool part. Well, I think is cool because, whatever, because I'm a physics guy. Here's what I think is cool. I could instead go like this. Y equals m. Okay, now right now it thinks m is a variable. So it just gave me that line again. It gave me a line with a slope of 1. But I go y equals mx. And now it's like, whoa, exclamation point. Wait, what? Did you just give us 2 variables? What are you doing, Abraham? What's going on? What's going on? But it's giving me an option. It's saying, oh, wait a second. You just gave me 2 things that could be variables. Should I assume the computer's asking me when it says, hopefully you see, it says add slider m? It's saying, hang on, is m, should we make a slider for m? Are you saying that x is going to be your variable and m is going to be some kind of adjustable parameter or some adjustable constant? And I'm going to say, yeah, dude, that's exactly what I have in mind. Thank you for realizing my needs. So what does it do now? So what it's doing now, it just made a slider for the value of m. It's treating m as some sort of constant or parameter or condition. It's treating x as the independent variable, y as a dependent variable. It's all in black, so it still has nothing to do with my green dots, but it's giving me a slider for the value of m, for the value of the slope. So now I can use this slider that hopefully you're seeing. Right now, the slider is set to a value of 1. So it's giving me a line with a slope of 1. But if I start playing with this slider, I'm making the slope. See, now the slope is 2.1. Now the slope is 2.5, blah, 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 blah. Or I bring it back. So now what I try to do is, if I think those green dots are in some kind of a line, but I don't know what the line is, i.e. I don't know the slope of the line, I just bring this until it lines up as best as I think it can with the dots. Now, I don't think this is good yet. I'm going to bring it over, and I can even, like, I can be more, sorry, I can make it more precise, like, oh, sorry. Sorry. That slider, sorry, I'm going back to, okay, here's my slider, M. Okay, I'm bringing it down, I'm bringing it down. I'm bringing it down. And it's getting better, but that's too small. So first of all, I can, I can zoom in on the graph even more, hopefully without losing you guys. Sorry. Okay, yeah, I'm zooming in a little bit more. I'm doing that with 2 finger, with a 2-finger spread or whatever you call that. Okay, that's about as much as I can do. Also, I think this might zoom into this. Yeah, okay, that zooms in more. Just, your typical stuff. And sorry. Okay, and right now M is at 0.1, right? And I still think that's a little too high. So you see what I'm doing though? I'm saying you physically, I drink too much coffee, so my fingers are going crazy. But I'm saying you can physically adjust the line until you make a slider and you can physically adjust the line okay, now I can be more precise. Yeah, I'll do it one more time. Do one more time. Okay, I keep skipping steps, but what I want to see if you see is this way I can actually fit the line to the data myself. It's a little bit hard right on. Oh, I'm looking in the chat and it's a little, oh, cool. Oh, thank God, because I was actually losing faith. All right, I think it is really cool too. Thank you. I'm looking at the chat and thank you. I think it's cool too. And I'm sort of blowing it now because like with the Zoom and with the delay, with the, what do you call that? With the delay and with me drinking too much coffee, like I'm not getting it as precise as I want. But yes, the whole point is you find the line yourself. The whole point is you can physically adjust until you see the slope. And you notice right now, like, I don't think the line is good yet. I think it's above all the points. I want to bring it down a little bit, and I'm playing with that. But right now, if I were to copy this down, I would have an equation for this line. I would be saying the line is y equals 0.1 times x, which in the case of your specific variables means t equals 0.1 times the square root of m. Do you see what I'm saying? Like, literally, this would give me the equation of our actual data. The computer doesn't know. I'm just trying to fit this black function to this green data, but I'm trying to do it physically with these sliders. And hopefully you can also see that even as so it's saying 0.1, if I try, even if my fingers are getting all jumpy, now that I've gotten sort of close with 0.1, I can just take an estimate now and do like, all right, let's try 0.07. Or okay, there we go, like, or 0.06, right? And that's a lot better. Now, in fact, now that I'm doing this with you, really, let me say even this line right here that I just got, which is a lot better. I'll zoom out, I'm gonna zoom. Yeah, this, and again, I can't really tell what you can see and what you can't, but look at this line that I just got, certainly a lot better than the others. Certainly a lot better, but I want to caution you, this line, I'll try to zoom out again. Or zoom in, I mean, okay, yeah. Oh, and I can do it this way. So. All right, this line that I have now, a lot better than the other ones I was playing with. In fact, this is a perfect example. Okay, so this is actually working. This line that I'm looking at right now, it really demonstrates everything that Ashton and others, I forget who, like a bunch of people were talking, it super illustrates why everybody feels so squeamish about that green dot that's off the line that's near the coordinate 12, right? Like if I use this line, it really calls out that one dot as a major outlier. And the reason it calls out that dot as a major outlier is because the line so blatantly perfectly goes through many of the other points. But I have to honestly tell you, like, maybe that one dot is an outlier. And what would we really do if we were really doing this for like a grant money or for the government or for a Nobel Prize? We would not make a big essay about how that one dot was an outlier. What we would really do is redo all the data over and over again. Because honestly, like that dot might be an outlier. And so maybe we did something wrong on that one dot. And the most honest way to see that is if we just redo the whole experiment. We could do that. We could redo all the data again, doing the same, picking the same values of M, and then redoing everything to see what values of T we got. We could do that. And if you have time in a lab, go for it. If you think one dot is so blatantly weird that it means something went wrong, you can't just redo that one dot. That would be lying. That would be fudging. That would be assuming a conclusion that you're trying to fit your data to. But if the one dot seems so bad that you think something went wrong, then fine, you redo the whole experiment, you take all the data again, and often we do have time for that. But if you can't do that, what I really want to tell you all is one of the reasons you think that that one point is so bad is because it's bad, it looks bad if all the other points were perfectly put on the line. But that's almost too good to be true. There's no reason to assume. You don't want a line that actually literally connects through every point. That's actually sus, to use, so to speak, to use the language of what's it called? Among Us, right? It's actually sus. If every one of the, I'm just trying to be cool. If every one of the dots literally is on the line, or put another way, if you pick a line that literally goes through and touches every one of the dots, something is weird about that. What you really want, like this line that I'm looking at now, is a lot better than all the other ones I looked at. And I did it by feel at first with my hands, as you saw, but then my hands, the feel of my hands wasn't good enough. So the feel of my hands, so I'm opening this again. The feel of my hands got me to a slope of 0.06. What I really think now is, okay, my hands are too clunky to use the slider now, but I've used the slider to get perspective. I think, honestly, I should be putting in something like, yeah, like that, like 0.05. Hopefully you can still see 0.05. You notice now, I got closer to that one. Or actually, I'm going to do even better. Oops, sorry. Yeah, now this 0.045. If you look at, so in other words, I'm saying the equation that I'm going with right now by feel or whatever, I'm saying right now what seems to be the line here is y equals 0.045x, which in the terms of your experiment really means that right now I'm thinking that period measured in seconds equals 0.045 times the square root of mass measured in kilograms. That's what I'm saying right now. Now, this line, and I think it's the best line that I've picked thus far of anything I've said so far. What I want to emphasize to you, and I apologize, we'll get to the homework, but first of all, hopefully you're seeing how to use decimals. And yes, I think it is really cool that you can do this. And it's really easy once you, it's not bad, like once you know it. But notice that I'm favoring a line. I just made all the other dots worse. I'm not the dots. I made the interaction between the dots and the line worse in order to make that one dot better. In other words, now I have a line, and I do see this thing's going through the chat. I'm going to go to the chat in a second. I think it's better. This line is better because no dot is perfectly on it, but we're getting closer to a situation where a bunch of dots are above and a bunch of dots are below. I'm actually going to go one step further. I'm going to look in the chat in 1 second. Sorry, I really will. I'm going to go a step further. I'm going to go even further. And obviously, if your fingers are better than mine, you can do this with your fingers with the slider. No. Oh, and it's even doing it in real time. I didn't realize that. It does it even before I press enter. So yeah, now almost there. What I'm trying to do, I don't know if you see what I'm trying to do is inch my way towards a number where actually of those 6 dots, what I'd ideally like is 3 of them to be a little bit below the line and 3 of them to be a little bit above. In other words, what I'm saying is you want a line that averages out all your data. When you think that one piece of data is really, really bad, it's because you're tacitly, not you, anybody, when they think one piece of data is really bad, they're tacitly assuming that all the other data is really, really good. But all data in general is only so good. So what we're looking for in trend lines is a trend line that cuts through the middle of all the data. And then we call that our line. And so you feel your way in with these sliders, and with the slider gives you a sense. And then, and everything I'm doing right now, I'm going to do one last thing. Then I'm going to look, let me. So so Remy's question is good. Is there no way to have the computer automatically get the equation like Excel? No, that's what Excel's for, to do it automatically. But I'm actually saying that what's good about, there may be a way, but I'm saying that what I actually like about decimals, and what I want us to actually get more used to is it allows you to see, it allows you to actually do the science, which I think is really important, because so I'm not saying get rid of Excel. And yes, there probably is a way for this to automatically do it, but I actually think that part of what we're trying to learn here is what it means to fit a line. One quick last thing. All of what I'm doing right now is assuming that I believe that the line is straight, but so assuming that the line is straight, I'm trying to get the best version of a straight line. But with decimals, you don't have to assume that at all. If you think that the dots are actually falling in a square root or a square, you could do that. And now see, in other words, you could put in a square root function and it's curved and then slide that around until you meet it. You could put in any kind of function you want that you think the data is corresponding to, and then you fit the data you fit the curve to the data. Now, again, I mean, yes, to be honest, this is a different, I think it shows more what's going on. And I would like us to get used to it. We could still also keep Excel in the running. But the real thing I'm trying to emphasize now, and I will, is that a best fit. Okay, I'm going to turn off the. Well, wait. Okay, wait, but let me get rid of that. Okay. Okay, getting back to that, and we said we were guessing that M was like 0.04. I don't remember. 0.039, yeah, something like that. Okay. Yeah, so that's my best fit line for the moment. Now, I know we have to get to the homework, but if you do this, if you do something like this with Desmos, if you put your scatter plot first, then you put a best fit line to it, then once you do something like this, then you're in a position to do the big main thing that you got in, that I think Mercedes introduced to you last week, that we're trying to fold into our analysis over time. I think now you'd be in a position to literally analyze the relationship between the dots and this line and see if they're good enough to accept or bad enough to throw away. Like, again, the ongoing question of how good is good or how imperfect is imperfect. The thing that you would do now, that I know we're actually running out of time today to get into too deeply, is you would bring back up your table of values. Do I still have it? Yes, I do. Okay. Okay, what I have here, and this is something Excel definitely cannot do. I'm looking, and forgive me again, I know I'm going on. I have my data. I have what I think is the best fit line going through my data. It doesn't prove that this data is falling in a line. It proves that if the data is falling in a line, it doesn't prove anything. But I'm not saying that the data definitely is falling in a line. I'm not saying that the function definitely is right. I'm saying that if a linear function is right, this is the linear function, right? You see what, right? I'm not saying the data definitely has a constant slope, but I'm saying if the data has a constant slope, this is a pretty good approximation of what the slope is. Now, so what? What do we do with that? What we do is, now that I centered the line as best as I could between all the data, now I pick the point that you think is the worst. Okay, now I'm going to say this once. We're going to say it again a lot next week, but I'm going to say it once. Maybe hopefully take notes if you can. I don't have I can't share 14 screens at once. But I would now go to the point that looks the worst, the one on the 10, and it doesn't even look that bad now, by the way, I don't think, but it looks like it's above the line. It doesn't look like it's on the line. So it's the one that makes me the most nervous. Like, okay, is that off the line by enough to throw out this line, or is it close enough to the line for me to keep this? How do I know? Here's how I know. Sorry, raise your hand again if you're still with me at all. I know this is all getting thick, but just raise your electronic hand if you're still sort of following where I am with all this. Thank you, Marina. Thank you, Giselle. And I can only see some of you, but okay. The rest of you, okay. Thank you, Giselle. Okay, cool. I know it. Like Sue Lady, Abigail, you guys are with me. I mean, I will turn off the screen and I will. Thank you, Sylvie. Okay, cool. All right, that's good enough for me for right now. So this is what I would do if I'm looking at this thing and I'm like, all right, number one, I would compare it to my other graphs, and if it's a lot better than the other graphs, that tells me something. But number two, I look at that point 10, and I say, okay, according to my data over here, an M coordinate of 10 yields a T coordinate of 0.532. That's according to my data. 10 maps with 0.532. But now I have a line here. This line has an equation. The equation is t equals 0.0395 times m to the square root. So what I would do is I would plug, and follow me on this, please write this down or something. If I want to see how good this line is and whether it really is a line or not, what I do is I compare. I literally compare. I compare the seeming error or the seeming incorrectness of a point on this line. I compare that to the built-in uncertainty of my measurements that I knew from the beginning of this lab before I ever even had a graph to look at. Like, in other words, I'm going to look at how far that green dot is from the line. I'm going to look at how far it is. I'm going to look at how far off the t value of like the green dot that's at coordinate 10. It's off the line, right? What do I mean it's off the line? I mean that the data says that the t coordinate for that is 0.532. But if I plug 10 into the equation of this line, it's going to spit out something higher than, lower than 0.532, right? Like, and maybe someone could do it right now while I'm talking. I can't because I'm talking, but I'm saying when you say that the dot is off the line, what you mean is when you plug in 10, what you mean is that the actual t value that you got for 10 in when you collected data was 0.532. But if you plug 10 into the equation for that line, you're not going to get 0.532. You're going to get something lower than 0.532. What you do is you write down those two numbers. Like, please write the 10. You write down the numbers 0.532 and the other number, whatever the equation spat out. Maybe I should do this right now. I'm worried about doing it and getting myself distracted. But you write down those.
I have the point if you want it.
Oh, yes, please. That'd be great. Thank you. Yes, please.
For 10, I got 0.63, and that's rounded.
Great. Perfect. Okay. First of all, thank you so much for paying attention. Totally submit for perfect. That's great. You're totally with me. Okay. Great. So I think that was Ashton, right? I can't see your faces, but that was Ashton.
Yes, sir. That was me.
Yes, sir. I love it. All right. All right. Okay. So what Ashton is saying, and again, please forgive me if I don't get to the homework today. That's the next class. Remember, we don't have a lab again, right? For next week. So next class, I'm going to tell you right now, because Remy was right to bring it up. Like, I'm going to keep 2 promises and break 1 promise. I'm going to tell you right now, because this is important enough. I'm going to finish this point. If there's still an ability to let you go a little bit early, I will. Next period, we're going to start right away with just going over the homework. And also, you won't have any new homework for then. Okay, so I apologize if we're not getting to the homework today. Next class, we're going to start straight up with the homework. There's not new homework. I appreciate that you guys have been struggling with it, and you're getting lots of points for it just by struggling. So just forgive me. I want to just I don't want to get confused. So we're going to make sure this point is clear. And next time we will start right away with the homework, and you won't have any new. I hope that's okay. And we'll still try to get out of here a little bit early. What I'm saying right now is that 10 from your data spits back 0.532. But from this line, according to Ashton, she's saying it spits back 0.6. Wait, I do have a question about that. The line spits back 0.6. Wait, can that be possible? You're saying 0.6, but 0.6 is lower. So I do have to pause for a second. You're saying 0.6. That's less than 0.5. That's a little confusing to me. Wait, you're sure about that? You say when you plug in, so if you take, in other words, if you take the square root of 10, you take the square root of 10 and you multiply it by 0.0395, you get, maybe I should do this. Okay, I'm going to do this.
Well, the points on the S, we square rooted before we did the graph. Like, those are our original numbers.
Oh,
and
good
then
point.
We square root them and got those for the X
Oh,
value.
excellent point. Excellent point. Thank you.
So,
Excellent point. Absolutely correct. Thank you. So wait, so then when you take 10 and literally multiply it, so if you take 10 and then you should just literally multiply it by 0.0395, which means you would get 0.395, right? If If you plug it into the, so it's my bad. I shouldn't have said the square root thing. You're absolutely right. Like according to this equation, the equation of this line is that the t value is equal to the slope 0.0395 times whatever is the x value, right? So this I can do in my head. You're right. The square root you've already taken into account. You're absolutely right. So I'm saying according to this line, if I zoom in, let me zoom in a lot. I'm just looking at that one special point that we're all bothered by, this point. And I'm moving over.
I might have put it in like wrong. So if you don't worry about telling me if I'm wrong, you know, I don't mind.
Okay.
So,
No, I appreciate you're very kind. No, and I know exactly what happened. You did exactly what I said. You did write what I said, but then you just made me realize that what I said was more complicated than it needed to be. So we can all look at this together. No, you did clarify. You're good. You're good. Well, thank you for your politeness. Here's what I'm saying to everybody. I'm trying to zoom in on that point as best as I can. And remember, that point is the bothersome point. Like this is the point that makes us all wonder, like, is our line good or not, or what? Well, look, if we zoom in on it, if you're not an idiot, there it is. There it is. Okay. Yes. This is what I'm trying to say. There's that point, right? Hopefully you can see it on the screen. There's that point. I don't know if you can see the axes, but remember, the x coordinate at that point was 10, right? The x coordinate at that point was 10. And in our data, you guys said that the y coordinate that you actually measured was something like 0.532 or something like that, right? But now we look at the line. Look at the line. Well, first, the line is below 0.4, right? The y value, the t value, according to that, if you just look at the line, what's the y value of the line at the x coordinate 10? Well, it's like it's less than 0.4. It's like 0.395, not coincidentally, because the equation of our line is y equals 0.0395 times whatever the x value is. The x value here is 10, so we multiply by 0.0395, we get 0.395. Is anybody still with? I'm saying right now what I'm trying to say, and again, I promise you, for good or for bad, as long as we can get to the end of this point, we will not start the homework today, but you won't have new homework. As long as we can all hang together and get the end of where I'm going with this, we'll be good for class today. So are people still with me? Like I won't even ask that yet. What I'm saying is right now, if you look, oh, can I even write on this? Maybe I can write on, yeah, maybe I can annotate. Hold on. Yes, I think I can. I'm saying. I'm saying this point here compared to here. I'm saying that the point according to your data is the point 10 comma 0.0395, I think. Or I mean, I'm sorry, I'm seeing 0.532, I think, something like that. Tell me if that's wrong, but I think that's right. But down
that's right. Yeah, you're good.
Thank you. Awesome. I love this class. Right, that's according to your data. That's the point from your data. But now, if you look at what the line is saying, is, well, no, the line is saying that if you put in the x coordinate of 10, according to the line, you're getting something even lower than 0.4. Where do I get 0.4? I'm just looking, I'm taking my eyes over to the left where the y-axis is, and it says the number 0.4. And specifically, if I plug into the equation is t equals 0.0395 times whatever the square root of your m is. Like the slope of this line supposedly is 0.0395. So you multiply 10 by 0.0395 and you get 0.395, right? So I'm saying now, the two numbers that we compare, the whole question is, oh God, our data says 0.532. but the equation says 0.395. That seems like it's off. Our whole question is, well, is it off by a lot or a little? Like, is that enough to care or not enough to care? Right? That's the issue here. And it's a very important issue. So what do we do? How do we know? We need something to compare it to, is the answer. Like, there is an answer to this. It's not just a vague thing of like, it seems okay. It's okay. Like, no, like the question is, so what we do, and so maybe some, so what we do, hold on. What we do, I wish I had more screens. Okay, you know what? I'm going to switch screens now and do this on a board. And again, this is the last thing we're going to do today. I'm going to set up my other board so you can see but everybody sees where I got those numbers from, right? The whole issue is our whole life issue now is how far off is 0.532 from 0.395? Like, how bad is that? And the answer is this, as soon as I can switch boards, or the answer of how you know how bad it is this. Okay. I'll explain what I'm doing. So just do me a favor, write this down, obviously, and I'll explain what I'm doing. Well, you might recognize what I'm doing. I'm looking at the percentage error so far, right? I'm saying, okay, this is our error. We measured it to be 3.395 seconds, but our like model or our conclusion or our whatever seems to imply that if our model was correct, it should have been 0.532 seconds. So apparently we're off by about 0.137 seconds, but there's still the question of, well, how bad is that? Well, 0.137 seconds divided by 0.532 seconds is approximately 0.258, or in other words, approximately 25.8%. Now that seems pretty bad, actually. And I'm being conservative because I picked the worst dot and all of that, right? Now, so far what I'm saying is that our worst piece of data seemed to be 25.8% off, or 25.8% error, you could say. Well, I don't even want to say error. It seems like what I'm saying is our worst piece of data was like 25.8% off of what our model says. That's what I'm saying so far, but that's just a statement. I'm not saying it's 25.8% off the correct answer. I don't have a correct answer to compare this to. There's no textbook value or anything like that. I'm just trying to figure out what the correct answer is. I'm trying to figure out how good my work is. So the question is 25.8, so I'm going to write off our model. The key question that I'm just going to answer, and then I'm going to give one big answer to, and then and then we'll pause on all this. The key question is bad compared to what? If your worst data is 25% off of the model, how do you know whether 25? What do you compare 25.8% to know whether your percentage is reasonable or not? And it does sound like a pretty high percent. By the way, I mean, it does sound high, but what do we compare to? We don't compare to other experiments. We don't compare to a textbook values. We compare the threshold of goodness or badness, the thing that we compare this to is how precise our measurements could possibly have been from the start, not how precise or accurate our measuring activity was. Like, not how much cup of coffees, not how much coffee we drank or how much we argued with our lab partners or anything like that, but just how good was our measuring equipment from the start. And I mean something very specific by that. Now, and again, maybe, I don't know how much Mercedes did or did not talk to you about this at the beginning of last class. It's one of the things I was going to ask you before, but I know we're running out of time now. And if she did talk to you about this before class, she probably went in a different order. I'm sort of going backwards on this now. I'm taking your data, looking at it, looking at the margin of error in it or whatever. And then I'm saying, do I have anything kind of objective or independent to compare this to? And the answer is yes, I do. Like, I'm saying every measurement we make already has built-in uncertainty. Even if we are, as human beings, don't make any mistakes, the measurement can only be as good and precise as the measuring tool. So, for example, well, here. Well, yeah, yeah. Now, I don't know exactly what stopwatches you were using or whatever. I'm just using this as an example. Say you have a stopwatch, right? And it gives you readouts like such as, or whatever. This is just an example. I don't actually want to use a 5. So let's say, okay, I'll use an 8. I want to be more random. Say you get a readout like 60.08 on your stopwatch. that means it's telling you things. It's telling you a number of seconds, and then it's telling you a number of tenths of a second, and then it's telling you a number of hundredths of a second, right? But that's the number of significant digits it's giving you, right? Well, the really important point here is, again, if Mercedes already said this, like, good, but I'm trying to put it in perspective now, that no matter how well you use that stopwatch is not telling you anything after the 8, right? So when it says 60.08, it's literally saying we have no idea about thousandths of seconds. We just know about hundredths of a second. So what it's literally saying is that it's really giving you a range. It's really saying when it says 60.08, it's saying it could be 60.081 or 60.082 or 60.083. Like, it's not telling you. It could be any. It's not saying it's 60.080. It's saying it could be 60.080 or 081 or 082 or 083 or 084. Now, probably not 085, because if it said 085, then it would have said 0.09, right? But similarly, in the other direction, 0.08 could mean 0.079 or 0.078 or 0.07. And I'm not saying because we made a mistake. I'm saying literally we only know what it's saying to that digit. So what I'm saying is literally, and I'm watching the clock, I will still try to get, but I'm saying if your stopwatch goes to the hundredths of a second, what you're saying literally is built-in uncertainty of plus or minus 0.005 seconds. Like, that could be 60.08 plus anything up to 005, like above it, or anything below it by point. In other words, a plus or a minus half of the amount of the next significant digit. We literally don't know. This number is really anywhere. 60.08 really means it's anywhere between 60.075. It's anywhere between 60.075 and 60.085. It's anywhere between there. So there's a plus or minus of 0.005 on either side, necessarily right from the get-go, which means, and I'm just about done, I promise, which means that with the clock, just with the clock alone, there's a delta T, there's an uncertainty in time of 0.005, assuming your stopwatch goes to hundredths. I don't remember what your stopwatch does, but I'm just using this as an example. There'd be an uncertainty of 0.005 seconds divided by what? Divided by 60.08 seconds. And the seconds cancel. So the denominator is whatever I measured, but the numerator is literally half of the smallest unit of precision, or the most precise significant digit that this measuring equipment has. And if I do that division, and I promise we're almost done. I thought I lost the calculator. If I do that division, we get a very, very small percentage, and I'm not surprised. Now, what I'm saying right now is, if the only measuring equipment we used in the whole experiment was a watch, if we didn't also, for example, have masses that we measured, and we didn't also have, displacement that we measured, but if just on the time itself, if the only measuring equipment we used in this experiment was a watch, we would say in other words, from time measurements, we have built-in uncertainty of approximately 0.0083%. If the only thing we did in this experiment was measure times, we would go in saying 0.0083%, which is small because those stopwatches are incredibly precise. Notice, no matter how precise anything is, it's never infinitely precise. There's always some uncertainty. But if we were only measuring times, we would go in and say all of our answers have a point spread Like everything has a point spread from the beginning of 0.0083% in either direction. And what we'd be saying right from the start is when we get results at the end, we should never expect our results to be any more. We should expect our results right from the get-go to be within a point spread of 0.0083%. Like our results could never be better than 0.0083% because we already have that much uncertainty just in the clock itself. And the clock is the most precise thing we're using. If the only thing we were using was a clock, we would go and saying our uncertainty from measurements is 0.0083%. And that's what we would compare to the percentage that we got when we looked at the green dot versus the graph. If the only thing going on in this experiment were a clock, then I would say, whoa, we're allowed a point spread, an uncertainty margin of about 0.0083%, but our dot was off the line by 25%. I would say, 25 is big. 25 is not always big. It depends what you compare it to. But if you compare 25 to this, if this were the only thing going on, then I would have to say, even though I'm thrilled that we all got the right results and all of that, the truth is, if I'm being honest, if you were considering publishing your results or taking them to a Prism poster presentation, I would say if this was the only thing going on right now, I'd say, I like that you got a straight line, and in my heart, I think the straight line is right. But the truth is, actually, you've got spread of like 25.8% at the end there, and I can only, with your watch, I can only account for 0.0083%. So just based on this, just to be super honest and to go back to like a question from 2 weeks ago, just based on this, even though I think you did get the right answer, if I'm being honest, I would say, but your answer wasn't really statistically very reliable. Your answer was 25%, was 25, your answer, your model was 25% off your data, or at least your worst data, if I'm being conservative, and your measurements could account for 0.0083%, but that ain't anywhere near 25%. So and this has nothing to do with your grades or anything, I'm just trying to explain how this works. When you want to know whether something's good or bad, you compare the error percentage that you find between your worst data, if you're being conservative, and your model, and you compare that to the percentage of uncertainty that was built into your measuring equipment. If this was the only comparison I was making, then I would have to say our model actually wasn't statistically that reliable. We need to take more. It doesn't mean it's wrong. It just means I wouldn't publish it. It means I don't trust it yet. I would have to take a lot more data. Even it means, if I'm really being honest, even though I like the answer, I don't really have solid basis for accepting that answer yet. Now, thing is, I'm just talking about the stopwatch here. The stopwatch is usually the most precise thing we've got going on. Stopwatches are incredibly precise. You also were measuring masses, and that's going to actually have a lot more uncertainty than the stopwatch. And we go with the biggest uncertainty that there is. And there was also, you were measuring lengths. There's more going on here, and there's more rules I want to tell you, but this is my overview of how you actually like look at what you're doing as we get more and more into this course. How to know whether something's good or bad is you measure the error percentage at the end, but you compare that to the measurement uncertainties at the beginning. And that tells you in and of itself whether your model is at least statistically reliable or not. It is 7 o'clock. I know I'd like to, I'm going to stop the screen share. Hold on. Hopefully, and I will, and I know, again, there's no new homework. Everything you've been doing so far with the homework is great. Take a pause on it. And you're getting credit for what you tried. We're not assigning anything new. I'm going to start right in with the homework next time. And I do appreciate the efforts everybody's making, but just because I'm also trying to keep up with your lab and all that, I'm going to stop this screen share. Stop. And I'm just going to ask, I'd like to let you go like almost 10 minutes early, which is not huge, I know, but is the thing that I just said, that thing about uncertainty, it's just a first pass. It's like the first big look at it. Well, two quick questions. One, does it make any sense what I just said at all?
Yeah.
She's like, yeah. Okay, cool. Oh, thank you, Sylvie. Okay. And it makes it, okay, cool. And did Professor Talley explain this sort of like in her way at the beginning? Or, I mean, have you seen, that's a yes, or that means this makes sense. So Jonathan and Jake, you're saying yes, she did, or this? Okay.
Yeah, Mercedes had a whole like paper that she put out about uncertainty that she gave us when we started the lab.
Awesome. That's awesome. And does this contradict any of that, or does this seem consistent with what she was saying? Like, does it? Okay. All right. Okay. And look, again, we're being honest with each other. I'm saying honestly, just based on the little thing I just did. The weird thing is, even though I love your results, and I think your results are much better looking than you think, according to this little analysis, it means your results are not ready for publication yet. Like, just being honest, it doesn't have anything to do with your grades. I mean, your grades are fine, but this is the metric, or the first pass of the metric we use. Okay, I've said enough. If you're okay with the fact that we're just going to postpone the homework analysis another week, if you're okay with that, I'm okay with leaving 8 minutes early. It's not huge, but it's 8 minutes. Are we? If you're good, I'm good. Are we good? Okay. All right. So cool. I mean, I'll hang out if there are any questions or anything. I'll hang out until you go. But goodbye. Okay. Have a great week.
Have a good night.
Have a good night. Have a good night.
I have a question about the extra credit games. So, so if I submitted them, but they haven't been graded yet, some of them are graded, some of them are not. Is there an option to submit for the second week for the same game, or would that not be possible until the first one's graded?
Wait, that's a really good. I could have sworn I did. Hold on. No, first of all, yeah. Okay. The simple answer is if I ever, thank you, Sylvia. Thank you, Sylvia and Giselle. Wait, that's a great question. The first answer is if and when I ever fall behind. No, you always can still keep going, even if you didn't get it back. You should always just keep going. And sometimes I do fall behind, although I didn't think I did. Did I fall behind with yours? Hold on. I'll do yours right now.
Okay, yeah. Because if there's an option, because I wasn't sure if there was an option to submit like a second document for today yet, or it would, because I was thinking it would make me unsubmit it before I submit another one.
Oh no, wait.
If the first one's not graded.
Wait, great question. No, definitely a great question. But and there is a new one for today. It's been posted. Like each day is a different portal, so it doesn't so even
I was thinking that like you can redo the same one every week.
Oh no, a new portal opens every week. Like if we're talking about just the regular one, like there was turn one last week. Let me look at yours right now. Did I not give it back? I could have sworn
the avatar one.
Oh, for that stuff. Oh, that's
yeah.
Okay. For that stuff. Okay, I'm sorry. You're right. For that stuff, I don't open up a new one every week, but but I'll do yours right now. But if you keep uploading without unsubmitting the old, which it does let you do, you can upload new things without unsubmitting the old. I'm pretty sure.
Oh, I didn't know that. I was thinking it would make me unsubmit the ungraded one.
We could try that right now, but I'm pretty sure it doesn't. And then that way, even if I fall behind, whenever I do open it, I'll see everything. But oh, you're right. But I'll do yours right now so there won't even be confusion. Hold on, I'll do it right. But yes, you can just keep doing it each week and you'll get the points for each week, one way or another. Okay, and I see this right now. No, you're absolutely right here. Okay, hold on.
It's the one with the dog.
Right. No, I love it. That's great. You should get points for that. Absolutely. And
I know Lizzie's adorable. She if she was in the class, she would have 1,000,000 points.
You're right. What's her name? Lizzie, you said?
Lizzie, yeah.
Awesome. Okay. So tell me in 1 second, you should see. Okay. Oh, from Korea. No. All right. Tell me if you see it on your side right now. Oh, yeah. Tell me if you see it on your.
I'm going to check right now. Yeah, 7 out of 7.
Right. Okay. So perfect. So now you can just keep uploading to that portal. It shouldn't take it away. And even if it shouldn't, and I'll just keep accumulating the points.
Oh, awesome. So every week I could submit the avatar one.
That is correct. Absolutely. Yes.
Yay. So every week there's going to be a new photo of Lizzie.
Fine. I'm down. That's fine. That's great.
Okay. Thank you so much for clarifying. Have a good night.
Thank you so much. Have a great night.
Thank you. Bye.